In this video, I want to take a look at how we actually compute eigenvalues. So the situation is we've got a square matrix A, and we want to find values lambda so that, I don't know why I have that written out as lambda and not as the symbol lambda, but there we go. We want that ax to equal lambda x for some non-zero vector x. Certainly 0 works for any lambda. But we want to find the special ones. We want to find the lambdas where you got some non-zero vector that makes that true. So here's what we're going to do. We're going to take the stuff on this side of the equation and subtract it off over to the other side, which looks like this now. And what I want to do is I want to factor the x out. But I can't just do it straight away because then I'd be left with a minus lambda inside the parentheses. And that looks weird because a is a matrix and lambda is a number. And what do you mean by a matrix minus a number? So in order to get around this, what I'm going to do is I'm going to slip in the n by n identity matrix I in here. So rather than x, I'm thinking of it as I times x, and then multiplying that by lambda. Okay, I times x is x, but what I can then do is rather than thinking of I times x, I can think of it as lambda times I. So rather than this matrix here having all ones down the diagonal, it has all lambdas down the diagonal. But then I can now factor that x out because A is a matrix and lambda times I is a matrix. So the distributive property allows me to pull this out, A minus lambda I times the vector x. We want that to equal the vector 0. This is something we've been dealing with all quarter. This is a homogeneous system of n equations and n unknowns. And we want a non-trivial solution, right? Sure, x equals 0 works. X equals 0 vector works, but is there something non-zero that works? Well, we know that if this matrix, A minus lambda I, is invertible, then there's only the trivial solution. So what I want to do is I want to find when A minus lambda I is not invertible. And I know that that's equivalent to all kinds of things, right? One of them being it's non-invertible if the determinant is 0. So I have an equation that I can now try to solve for lambda. This equation is called the characteristic equation, and as it turns out, we'll see it a little bit, it turns out to be always a polynomial equation. So here we go. Here's an example. My matrix is 2 by 2 here, matrix 1, 9, 2, 4. So A minus lambda I looks like 1, 9, 2, 4 minus lambda times the identity. And so when you multiply the lambda times the identity, it's the lambdas on the diagonal. And what happens is you just get the minus lambdas on the diagonal, right? So I have a 1 minus lambda and a 9 minus 0, a 2 minus 0, and a 4 minus lambda to get that matrix. Now, I want to point out that the book actually does this backwards from the way I do it. And maybe you're not surprised that I do things differently from the book. That seems to be a theme in a lot of my videos. Right? That is, what they do is they start with this equation, and rather than subtracting the lambda x over to the other side, they subtract the ax over to the other side. And so rather than ax minus lambda x like I have, they have lambda x minus ax, and the stuff that I end up in parentheses is lambda I minus a. It's exactly the minus of what I have. Well, fine. If you did it that way, then you'd have this stuff minus that stuff. So this diagonal would be lambda minus 1 and lambda minus 4, but this would be a negative 9, and that would be a negative 2. You got to remember all those extra negatives. I find it simpler just to subtract lambda from the diagonal, and it's quick and easy that way. Now, there's a reason why they do it, and we'll run into that in a subsequent video, but it really doesn't make that much difference. To me, it's easier to do it this way. So take this determinant. It's 2 by 2, just product of the diagonal here. 1 minus lambda times 4 minus lambda, and then minus the off diagonal, so 9 times 2 is 18, but I'm subtracting. Multiply this out to get 4 minus 5 lambda plus lambda squared, and then minus 18, which looks like lambda squared minus 5 lambda minus 14 equals 0. I think I can factor that. Yes, I can. Lambda minus 7 and lambda plus 2 equals 0. So lambda equals 7, lambda equals minus 2. If I didn't see how to factor it, I could, of course, use quadratic formula. And so I have two eigenvalues for this matrix. One of them is 7, and one of them is minus 2. Okay. In general, for your standard n by n square matrix, right, it looks like this. When you do a minus lambda I, you just get the minuses on the diagonal. If you do it the book's way, the diagonal would look like lambda minus a11 and lambda minus a12 all the way down to lambda minus a(n), but then every other entry would have to have a negative sign and put in front of it because you'd be subtracting that whole matrix A. Right, so it's just a lot of minus signs to keep track of. Doing it this way, you don't have to keep track of as many minus signs. And then, of course, the characteristic equation would be the determinant of this thing is equal to 0. Because what I want is I want this matrix, A minus lambda I, to be not invertible, so we want its determinant to be 0. Okay. This will always turn out to be an nth degree polynomial equation. That is, when you take this, you're going to have this A11 minus lambda times a subdeterminant here, and then this times some subdeterminant. Anyway, eventually you're going to get this term times that term. All of those diagonals are going to be multiplied together, which will end up with a nth degree term for lambda. Now there's a couple of special cases where this is actually easy to compute, and here's an example. Here's a 3 by 3. Let's find the eigenvalues for this. So 1, 2, 3, 0, 4, 5, 0, 0, 6, the 3 rows there. I want the determinant of A minus lambda I to equal 0. So again, just the way I do it, just subtract lambdas from the diagonal and take the determinant, set it equal to 0. Well, the thing is, because this is an upper triangular matrix, taking the determinant is particularly easy, right? Because I'm just going to expand down this first column. So it's going to be the 1 minus lambda times this little 2 by 2 determinant, and then minus 0 plus 0. So you don't have to worry about those. And then this 2 by 2 determinant is just this times this minus 0. And so the whole determinant it ends up being the product of the diagonal entries. Now in this case, I'm not going to multiply it out because I know what I'm trying to do. I'm trying to solve for lambda, and it's already equal to 0. It's already factored, right? Generally, if there weren't a bunch of zeros in here, you'd have, like we did in the last example, you'd have plus some other stuff and minus some other stuff, and you'd have to multiply it all out and collect like terms. But in this case, where this is a triangular matrix, you got a bunch of zeros down on one side of it here, one corner. The determinant looks really nice. It's already factored, and so I can clearly see lambda equals 1, lambda equals 4, lambda equals 6 are the eigenvalues of that matrix. And notice the 1, 4, and the 6 happen to be the entries on the diagonal, on the main diagonal. Yeah, well, there's a theorem that says if A is a triangular matrix, then the eigenvalues are the entries on the main diagonal. Notice triangular could be lower triangular, or it could be upper triangular, or it could be diagonal, because diagonal is both upper and lower triangular. Okay. So there's the way we're going to calculate eigenvalues. Find the determinant of A minus lambda I, set it equal to 0, solve for lambda. Okay. Solving polynomial equations. This takes you back to your algebra days. Okay. Now that we know how to find eigenvalues, the next thing we need to do is to be able to calculate eigenvectors, and that is the topic of the next video.